Welcome to our middle video of the complete solution, solutio, I guess, solution to AX is equal to B. In this video, we're going to focus on matrices that have full rank and what that then tells us about our solution, and then kind of pretty much round up what this section has been about. Last video, we dove into full column rank, as well as just kind of the concept of the particular solution. And so what I'd like to do here, because I didn't fully outline the complete solution, I mostly focused on just XP and identifying what that was. And again, which kind of lended itself to talking about full column rank, because that's when we have just a particular solution. Is that today, if we allow full row rank, and specifically full row rank, then we're going to have short matrices that are wider overall. So we're going to have kind of extra columns, free variables. There's going to be more than just the zero vector in the null space. So we're going to have solutions to AX is equal to 0 that are in the null space that's not just 0. And so what that does to my overall complete solution is when I have AX is equal to B, the format for X will appear like this. It's my particular solution plus any vector that is found to be in the null space. And that would help identify and span that null space. And so again, in the previous video, this vector was only 0. And if that's the case, when we have a full column rank, again, if that is 0, then X is only the particular solution. So again, that's why we didn't have to worry too much about this. And so you'll notice in terms of our objectives today, we're going to start here. We want to know, okay, well, what's the complete solution? Let's identify these pieces, and we'll see this in the example when we start digging into full row rank. So, okay, kind of a shorter video. We'll kind of see how long it takes to kind of walk through some of this. The idea is to keep it short. And then the rest of this section, what I would like to do is part 3 for this video section, I guess 3.3, is to do the worked examples and kind of talk through those and work through and solve those a little bit more than just what's in the text. And expand on that. So hopefully you'll find that helpful and see a little bit more examples. And I'll speak to that a little bit more again later on. So when we look at this, I do kind of want to make the case of why this format works. And so let's say we're looking at my solution set here. Remember that the particular solution, XP, comes from solving AX is equal to B. So when I do A times X, if I do AXP, this should get me to my vector B. Remember that Xn are the vectors that solve the system when AX is equal to 0. So any vector that I multiply with A with from Xn that's in the null space should zero out, because remember that's the whole purpose of those vectors. And so if I take this expression here and if I substitute this into my system, then what this becomes is my matrix A times XP plus Xn. And if I distribute my matrix, we get A times XP plus A times Xn. Now remember, AXP, A times my particular solution, well, this is the vector B. And A times any vector that's in the null space is the 0 solution set. Creates a 0. And so notice that all of this is then equal to B. That this represents every possible vector X that we could have that would ultimately solve my initial system. And this is kind of, again, what I'll highlight in the example, is that these vectors here that are in the null space, there are many of them, because remember the null space is it's a space, right? And one of the properties of a space is that vectors can be multiplied by scalars and still be in that space. So when I identify a single vector that's in that space, then we can find every other vector in that space by multiplying or combining it with any other vectors that are there. And by multiplying, I mean multiplying with a scalar, not vector multiplication. And so notice that this actually can create, if there's another vector here that works, this can create an infinite number of solutions. And if you think back to the fundamentals of solving a system, whether it's linear algebra or algebra 2 or whatever, there are 3 ways when I'm solving this, so there's three cases, right? Three ways my answers are represented is kind of what I was thinking. And that when I solve this type of system, there can be one solution only. There can be no solutions, we get nothing. There is this matrix and anything here cannot get to this vector. Or there's infinitely many. And that's what we're kind of seeing here. That if this vector right here is not zero, if there is a solution, if there is a vector that is not zero in the null space, then that means there's an infinite number of vectors that can be added to my particular solution. And again, I'll kind of give you a picture here to kind of visualize this. He gives it in the text as well, but I'll kind of showcase that a little bit more at the end, I think. Because enough talking, let's actually get into a problem. So what you'll see right here up above, this is technically example 2 on page 107. And so I want to talk through this. He does the work as well. And just kind of work through this and again, kind of talk out loud of my thinking. And if it's helpful, hopefully it's the purpose of the videos. But if not, then you can obviously fast forward into the next section or the work examples. So when I look at a system like this, again, I notice that M is less than N. That if I create a matrix out of this, the coefficients here becoming my A, I get the matrix 1, 1, 1, 1, 2, negative 1, which ultimately I know that I'm going to augment with my vector B. Now, again, pay close attention to my matrix A, just A right here. That essentially it's a 2 by 3. So again, the number of rows is less than the number of columns. Now, what's going to be a little bit different from what we saw in 3, 3, 1 is that my R, the rank of this matrix, is going to be equal to M. So again, my rank is going to be equal to the number of rows. And this is kind of, again, what's referred to as full row rank. Full row rank. Every row will have a pivot in it. So when I take this, we want to walk through and put this into reduced row echelon form. Now, if this is the case, something that we'll see later is that if this is full row rank, every row has a pivot, then I'm not expecting any 0 rows. So again, from the previous video, when it was full column rank, it was possible to boil down to my 2 pivots, but then have 0 rows underneath. Because we're not full row rank, we're just full column rank. So the columns are great. They each have a pivot and the rows may not. In this situation, every row can have a pivot, but because there are more columns, then we could end up with a free variable, thus creating xn type solutions. We have a null space that's not just 0, potentially. So we want to go through and verify that. So first row, first entry, here's my pivot. Again, this is built to be a little straightforward. Just to write out my process, I'm going to do row 2, replace with row 2 minus row 1. So really straightforward. 1 minus 1, so let's just go ahead and fill this in. First row stays the same. I always have that bad habit of wanting to start the operations immediately. Just go ahead and keep my first row there. Because now I can walk through and fill it in. 1 minus 1 is 0. 2 minus 1 is 1. Negative 1 minus 1 is negative 2. And then 4 minus 3 gives me 1. So, first pivot, 0 underneath. We can move on to my next row and identify my next pivot. Notice, because again, this is just coincidence of the problem, consequence of the problem. There are no other rows underneath, so there's nothing to zero out. So we're in row echelon form. We want to put this into reduced row echelon form. So I want to zero out this entry above my pivot in the second row. To do that, we're going to do row 1 replaced by row 1 minus row 2. And I'll put this answer underneath. We'll get 1 minus 0, which is just 1. 1 minus 1, which is 0. 1 minus negative 2, which is 3. 3 minus 1, which will give me 2. Second row, 0, 1, negative 2, and 1. So this is our ultimate R. And forgetting the notation they wanted to use instead of D. Instead of B, they did call it D. I was starting to freak out. This creates my D in terms of my augmented matrix. So how do we read our solution from this? Like, that's the big question. We talked about it in the previous video. If I want to find the particular solution, we're going to let any free variables be 0. Be 0. So when I'm looking, I have a pivot in the first column, I have a pivot in the second column. It means my third variable, this is x1, x2, and then x3, I'm going to let x3 be 0. If I do that, imagine this column is no longer here, then what this vector D is giving me is the solution to x1 and x2 immediately. So that means I can actually fill out my solution for xp as 2, 1, and 0. Now if you took this and plugged this in for x, y, and z, referring kind of back to the normal variables, 2, 1, 0, well that's 3. 2 plus 2, 0, 4. Notice how this solves this system, but it's not the only vector that can solve this system. Thus, the need to find xn. There's a null space. We zeroed it out, but what if we don't zero it out? So thinking back to 3.2, if I want to find the null space, if I want to find the vectors that span that null space, we find it by letting one of the free parameters be 1. We let any other free parameters be 0, but we only have 1 this time. And now when I do that, remember, we're not setting it equal to 2 and 1. If I'm finding the null space, we're setting it equal to 0, and that's really, really, really important. So if I was to think about this augmented matrix, we're letting this be 0 because we're trying to figure out what are the vectors in the null space. Right? We're solving this system in this case. So when I solve this system with this for my x3, which is really z, we get that x1 is equal to -3, and I get that x2 is equal to +2. Remember from 3.2 how we're essentially just taking the opposite signs for these free parameters, these free variables, and that they will go in the place attached to the pivot. So because this is my pivot for x1, it means x1 in my free variable is -3. This would be then 2. And remember, we're letting x3 be 1. So what I have right here is my vector for xn. And I'll write that here. Okay, xn is -3, 2, and 1. So if you were to plug if you were to plug this in to here, it wouldn't be equal to 3 and 4. Right, if I plug this in, I would get -3 plus 2 is -1. Plus 1 is 0, because remember, this is the solution to ax is equal to 0. I'll say xn specifically. So what is the purpose of this vector? The purpose of this vector is that any scalar here ultimately is adding only 0 in terms of the overall solution, but it's creating that line and space that is actually the solution to this problem. Because z is a free variable, z can ultimately be anything. And the way that it's combined is if I want z to be something, x and y are scaled according to this combination. Now, how that combination works is built off of the complete solution that I wrote out before digging into this problem in particular. So let's say I erase this and this and this. Erase the original problem as well. The complete solution to that system would look something like this. My particular, which was 2, 1, 0, plus xn, which is -3, 2, and 1. This set ultimately creates my answers. Now, in here, and I'm going to see if it's listed, notice how there's no kind of scalar listed, and this can be kind of misleading because it looks like I could just add this, and then that would create a solution. But that's only true when x3, remember, is equal to 1. x3, or my z, is a free parameter. It can be any number that you want, and then we would just need to adjust these as possible. So how do we account for that? By literally multiplying it by that parameter. x3, z, you could put in a constant. And now this would represent every possible solution to that original system. I could set x3 equal to 4, 3, -1, -3. And if I go through and I do this to figure out a solution for x and plug those numbers in, it would solve the original system. So what does this look like? What is actually kind of happening here? It's like, okay, I kind of see what you're saying, but why necessarily does it have this format? Well, again, think back to what we've been doing in Unit 1, into Unit 2, into this unit now. We started with a matrix A, right, a system, a matrix A, that was 2 by 3. The solution set, you'll notice, is in R3. Now, this is a 3-dimensional vector. So we're looking for a solution set that is in 3 dimensions. Now, if you think back to the rank of this matrix, the rank of A was only 2. I had 2 linearly independent columns, if we think back to the column picture, which meant I had 1 dependent. Now, when that's the case, my solution set is going to end up being a plane, because I'm going to have these 2 vectors that are initially okay, and then this one that can change. So how do I figure out the equation to that plane and all of the points in that? It's based off of this. This is going to initially give us a starting point, and then this is what's going to slowly start to spread out the points and move them. The picture that's in the book, I think, can also help make things a little bit cleaner if we think more in general of x being xp plus xn. That if I'm starting at 0 and I find my particular solution, which is some vector, and this is some vector xp, from the origin, staying at 0, I'm going to get another thing for n. Now, what this is telling us is that if I add these 2 things, what xn is going to do is continue to add vectors and find points along a single line that runs parallel here. So xp takes me to this point, and then xn and all scalar multiples of it give me every possible solution along this line, along this plane in space, as we go into higher dimensions, whatever that higher thing looks like. But ultimately giving me an infinite number of solutions. And that's where things kind of get interesting and how we can connect them back into Algebra 2. Because when you think back to Algebra 2, we got infinite solutions when I had a row completely zero out. So that would create that free parameter, and that free parameter could be anything we essentially wanted it to be. And if that happened, if I can make it anything I want it to be, then I can technically find any point as long as it's in that space. Well, if it's anything, it's infinite. If there's no free parameter, then there's only ever one solution. There's only ever one point that would work. But the second we introduce this and multiples of this, we start to get an infinite number. It's why when we have a full row rank, where R is equal to M, this kind of gives us 2 options in terms of solutions. We can either have one solution, that can still happen, or we have none. Sorry, not none. Infinite. Infinitely many, which is what we're seeing here. We saw that yesterday when it was a full column rank. We could have one solution or none. We have all of these extra 0 rows, but if I still have a number in my vector on the other side, that can never be true. 0 can never be equal to 1. But here, if I'm getting a row of zeros with no trouble on the other side, or actually there's not even any extra row of zeros, we just have this extra column, then that can't happen. So no solution isn't even a possibility here, because again, my correction, even when I was thinking about it, right, if I'm full row rank, there is no extra row of zeros. There's no way this could have no solution. There has to be one, and if there's not one, then there's infinitely many. So hopefully this kind of helps a little bit. I think the worked examples hopefully will showcase a little bit more. He gives some properties for every matrix that has a full row rank, which can be helpful if you want to take a look at that. All rows have pivots. There is no R0 because there's no 0 rows. R0 is R. AX is equal to B has a solution for every right side B. In other words, there is an answer period when this is the case, right? You either get one or infinitely many. So again, what's kind of fascinating is in that original problem, when we set the right-hand side to 3 and 4, we could actually choose anything because xn will allow us to get to anything from that particular solution. We just need to figure out what the particular solution and what my starting point is. The column space of A is the whole space of Rm, and I think that's the next thing that I kind of wanted to hit on a little bit, and I talked about it a second ago when we were looking, kind of breaking this down, is that if I'm 2 by 3, again, the rank of this was 2 because that was my row rank, but row rank and column rank are the same. So that means the column space has to have the same dimension as the number of rows. And if R is equal to M, then that means the column space has to have dimension 2, M. So that means this must be an R2, must be an R3, 4, depending on the number of rows. Now again, we're assuming the extreme that it's a full row rank. Right? So we're assuming that every row, again, has a pivot. The last one, if M is less than N strictly, the equation AX is equal to B is underdetermined. In other words, there are many solutions. You'll see the equality set from earlier. We were looking at for the short and wide, if M is less than N. If M is equal to N, we'll only have one solution. I'm going to highlight that in a minute. But if M is strictly less than N, then this case is going to happen every single time. All right, we're going to have that free parameter because we're going to have that extra column. It's going to create something that's non-zero from that extra piece. Last thing I want to put up here, and this is, again, from the text, so it's kind of easy to see, but I think still to highlight because it's written kind of in a block matrix setup, which again can look intimidating at first. I haven't done a lot of block matrix writing during these videos, but I want to bring it up now. Which kind of runs case by case. So kind of putting together the first video 3.3 and putting together this video and then looking at some worked examples in the next one. And so there are 4 total possibilities here that can happen when we're solving AX is equal to B. We have 4 possibilities. Now, think about your matrix as being M times N. We're not just focusing on square matrices, right, but things that can be rectangular, etc. But if we do have M is equal to N, so what if I do have a square matrix? And in that square matrix, we are assuming that R is equal to M, which is equal to N. So the rank is equal to the rows. The rank is equal to the number of columns. If that's the case, then A is a square invertible matrix. It has a pivot in every row. It has a pivot in every column. It means we are able to solve any system. And not just that, there would be no free variables because there's a pivot in every column. And the pivot in every row ensures that there's no extra 0 rows. So there cannot be no solution. There cannot be infinitely many. This will always have just one solution to the problem. XP. Whatever that particular solution is, there's only one answer to that. And when you go through and take a matrix like this and put it into reduced row echelon form, outside of the augmented piece, you should always be able to boil this down to the identity matrix. You should always have a pivot in every column and every row, which means we can zero out everything above them and below them, creating the identity. So this is our first scenario. This is kind of where, again, chapter 2, chapter 1, we kind of looked at some other things, but we were kind of living in this square invertible world. Well, chapter 3, we don't have to live in that world anymore, right? We're expanding that. So in the next scenario, let's consider if the rank is equal to M and the rank is less than N. So if this is the case, what we're essentially looking at is m is strictly less than n. This is what we were just looking at. It means my matrix is short and wide. I have my identity matrix when I do my reduced row echelon form, but because there are extra columns, right, my rank is equal to m, but there are extra columns that are here, then there is some other matrix F that occurs. That could be a single column, it could be multiple columns, whatever, but this is the setup that we would get. We kind of saw this, I just didn't use F. But we used this in 3.1 and in talking about the null space. And if this is the case, then when I go through and try to solve this system, we're going to always have infinitely many. Always. And again, the idea is that if I have this strict inequality, right, it's not possible for m to be equal to n. If m is equal to n and I have full rank, then we can have one solution or infinitely many. Right? That's when we have options, and that's why the book kind of gives that. For the third one, what if r is equal to n? In other words, now, what if r is equal to the number of columns? So I have full column rank, but the number of rows is greater than the number of columns. So m is greater than n. Then what we end up getting is a tall matrix that is thin. Tall and thin, I think is what he calls it. So r is equal to n, but again, there are more rows than we have rank. There are more rows than we have columns. Then what happens, and again we saw this yesterday, I can still form the identity matrix, but now I essentially have a row of zeros sitting underneath. Because again, if every column here has pivots, then we can zero out everything underneath. But the issue is that I may not be able to zero out everything on the other side. So when this occurs, it is possible to then have no solution at all, or we can have one solution when solving AX is equal to B. Because if everything zeroes out to the right, then we're okay. It's going to be similar to this scenario. We just have extra rows. But if I cannot, if I get a non-zero entry, 0 cannot be equal to something non-zero. That's identifying that there's no solution here. We can get nothing to this system. We say that B, remember, is not in that space. It's not in the column space. That's what we would see. So these are my three options here. Now you'll notice there are 4 total possibilities. We've got full rank. So my rank is equal to the number of rows and number of columns. So this we'll call full rank. We have full row rank. So notice the specifics. This is what we talked about today. We have full column rank. This is what we talked about in the video that I filmed a couple days ago, but depending on when you watched it, possibly watching it today. Well, what happens if it's not full row rank and if it's not full column rank? And that's our last option. So I'm going to erase these. This will be the last thing for this video. So much for keeping it short. The last option is that what if the rank is less than m and less than n? So not every row has a pivot, not every column has a pivot. It's almost staggered throughout my matrix. Then what is occurring is that in my overall matrix that could be rectangular, it's almost a combination of the second and third case where my matrix is going to look like IF because I have extra columns and my rank there's not enough, but I also have extra rows. So I'm creating these 0 rows. So the question is kind of, well, what does my solution set look like when my matrix is like this? And he calls this just not full rank because you can't really call it short and wide or tall and skinny because it could be squared. Well, there can't be one solution to this. We've already seen that if one of these cases occurs, remember if r is less than m, then we can have, this is where I'm going to see if I can remember right off the top of my head. R is less than m, I can't because I'm going to freak out because of the video. Then we have a tall and thin, we can have no solution or one solution. If r is less than n, this is what we hit on today, then we can have infinitely many. So then the only possibilities are those two. infinitely many, or none. We can't get just one particular solution out of this. And it really boils down to that zero row. If I have a zero row and zero on the other side, we have infinitely many. If I have a zero row and a non-zero entry, we have none. So notice that it's all down to the reduced row echelon form. It's down to the same work when we solve systems from Algebra 2 when it was just 3 equations, to Algebra 1 when it was two equations, 2 unknowns. How many equations, how many unknowns, right? If you think back to even that in that conversation. Dr. Strong goes into a great conversation, I think a dialogue almost of how linear algebra is alive, it's fluid. When we are trying to solve systems, there are computer programs that will do this for us. Again, I took a numerical methods course, it was a numerical analysis course at Auburn, and the course 1 and 2 both dig into computer algorithms, efficiency, errors, iterations, how much memory one of these things holds. I also took a class during my master's program of looking at sparse matrices. So what if we have a 1,000,000 by 1,000,000 matrix where 85–90% of the entries are zeros? If you think about things like binary, which is zeros and ones, we could create lines of code that are just zeros and ones. And so if we're trying to solve a matrix that is containing just that, we don't want to do a bunch of operations on zero. It's a waste of memory. And so really what I'm trying to bring into focus is if you're using computer programs to solve this, we have a limited amount of memory. And so in getting creative in how we solve these kind of systems, he goes in and talks about how instead of solving every single column, there are advancements of focusing on randomized columns. Solving the matrix by choosing at random which ones we end up eliminating and walking through the Gaussian elimination process. And so it's kind of fascinating that if it's random, then that means there's different probability trees. It's chaos almost. Chaos theory kind of comes to mind immediately. And so what does that look like? And so I think it's just fascinating, some of these applications. So depending on, again, what you're studying and what you may be interested, linear algebra may be a primary focus. It may be an underlying focus of what you're doing. But again, it's very, very much alive. Again, hopefully this video helps. I feel like I rambled a ton. But hopefully it identifies a couple things, gives you a couple examples. If you are just interested in seeing some worked examples, the next video, the final one for 3.3, will get into that. I was just kind of looking, I think there's 3 total examples. I will work through those and talk about that process. Again, just putting everything together with the matrix that's a little bit larger. And we'll probably have that posted soon. It'll probably be something that I'll film tomorrow, just based off of time that I have. So thank you. Again, if you have any questions, let me know. If you're on the online class, try to take a look at some of the practice problems and just let me know if you have any questions on the summative. Thank you.